In the OpenSuperQ project, the great opportunity is that we have the best minds and the best researchers of Europe working together towards a common goal. We have a team of researchers building a quantum computer based on superconducting integrated circuits that is large enough to outperform classical computers, at least in some tasks. So in such a collaborative project, different kinds of organizations come together. The central piece of the quantum computer prototype is housed in a cryostat that uses liquid gases to bring these systems down to a temperature very close to absolute zero. The gray cylinder you see and the setup with the horizontal gold-colored plates is the cooling infrastructure that is coming from our partner Bluefors.
Bluefors manufactures dilution refrigerator measurement systems that are used to operate quantum devices at temperatures far below 1 Kelvin. And we are a key component provider for some of the state-of-the-art quantum computing experiments around the world. And so we are especially proud to support the development of a working high-performance quantum computer prototype right here in Europe as an OpenSuperQ partner. One of the big challenges is to send and receive a lot of signals to and from the cryogenic environment. And so what Bluefors is doing is to build scalable, modular, and high-density wiring infrastructures that can be used to solve these problems. The integration of the wiring infrastructure with the core cryogenic technology is so important in the experiments, such as the one being done in Jülich.
The elements that you see on the bottom of the cooling setup houses the quantum processing unit where the actual quantum bits are sitting. This is coming from our partners at ETH, the Swiss Federal Institute of Technology. Around the quantum processing unit, you see immediate connecting elements that are coming from our partner at Chalmers University of Technology.
Hi, I am Jonas Bylander from Chalmers University in Gothenburg, Sweden. With an OpenSuperQ, my team has developed the superconducting quantum processor as an integrated circuit. There's a lot of physics and microwave engineering and fabrication technology that goes into making this device. And we have achieved 2-qubit gates with fidelity in excess of 99%. So that is a technical requirement. It's a very good number that will allow us now to scale up to many qubits and run a quantum processor. We are measuring a multi-qubit quantum processor in the lab right now.
Above that, in a separate box, you see the readout system, an amplifier made by our partner at VTT in Finland.
Superconducting qubits are operated at temperatures only a fraction of a degree above absolute zero. And furthermore, already small amounts of added noise can destroy the information. So, to determine which qubits are zero and which are one with traditional room temperature equipment, we first need to amplify this very weak readout signal as close to the qubit as possible. Therefore, VTT is developing so-called traveling wave parametric amplifiers, which operate at such low temperatures and also get close to a fundamental quantum limit of added noise. In principle, these devices transfer energy from a much stronger pump current to this weak signal, while both of these waves are traveling along a chain of superconducting elements with nonlinear characteristics. And in this way, already a single device can amplify the signal of multiple qubits by a factor of 100, which then helps to make the interpretation of quantum computed results faster and more reliable.
And it's all connected by filtered separate microwave wires, which are made by Low Noise Factory. This filtering is really important to keep the temperature from outside out of the system. Next to the cryostat, we have the electronics rack, which contains equipment made by our partner Zurich Instruments, takes the commands and the programs that are coming from the programmer and translates them into the signals that the quantum hardware can process that are a lot more complicated. It also synchronizes the various signals, and it takes the signals coming out of the cryostat and puts them into a form that the users can use.
Zurich Instruments is responsible for the development of room temperature electronics and the control and measurement software of the quantum computer. Any quantum computer needs, in addition to the quantum device, classical electronics and classical programming of these electronics to control the device. Since 2018, we offer the first commercially available quantum computing control system that combines these electronics with the software. In the project, we are developing a new instrument for feedback in the system, new instruments for controlling and measuring the qubits with low noise and high fidelity, and a new software that enables scientists to do fast bring-up, frequent calibration and customization of their system. Combining all these tasks, we are developing a quantum computing control system which not only scales to large qubit numbers, but it allows researchers and engineers to focus on the quantum processor while they are benefiting from the most advanced classical control electronics and software.
And where you do not see anything is the software development infrastructure that is connected offsite from a separate room, which is developed along with the first applications from our partner, the University of the Basque Country in Bilbao.
Much like a classical computer, a quantum computer comprises hardware and software components. At the software level, we have both classical software layers, which for instance manage to control the quantum computer, and quantum algorithms. Quantum algorithms, which are composed of quantum gates, are at the core of quantum computation. They are a set of instructions which exploit quantum properties such as entanglement and superposition to speed up information processing. An important issue to remark is that not every algorithm can be accelerated in a quantum computer. So finding suitable applications is a key objective at OpenSuperQ. Within the consortium, we have explored applications in finance, quantum machine learning, and quantum chemistry, among others.
If we look at the world, a number of places in the world